So, in yesterday's class, we looked at the definition of noise figure as well as the noise figure of a cascaded system, right? So, quick review. You define noise figure as the total noise at the output of a two-port over the noise at the output due to the source resistance alone. So, as if it were the denominator is calculated assuming that the two-port or the block, cascade, whatever it is from input to output, it's completely noiseless, right? So, in other words, noise figure is a measure of how much noise, additional noise is added by your system, right? So, in other words, it behaves as a measure of signal to noise ratio, okay, degradation through the system. So, you can also write it as the input SNR over output SNR, okay. So, based on this fundamental definition, you can go ahead and derive the expression for the of a cascade of n cascaded systems having gains, power gains G1, G2 all the way to Gn and noise figures F1, F2 all the way to Fn. And what this is telling you is that the overall noise figure, okay, has a contribution directly from the noise figure of the first stage, okay, and then the noise figure of the next stage is divided down by the gain of the first stage, etc. Now this should tell you, this expression now tells you the reason for deriving this is to show you the need for a low noise amplifier, right? Clearly the first amplifier is going to add noise directly, right? It better amplifier if you want to maintain good SNR when you go through the cascade. Number two, it better have good gain, okay, G1 better be high or A1 better be high because you need to make sure that the noise of the succeeding stages is attenuated. Otherwise, there's no use being with a gain of 1, okay, because the noise of the next stage will immediately get added up. Make sense? Okay. So, the Freeze equation tells you okay, kind of indicates the need for a low noise amplifier. Okay, and as we go through the course, you will understand the need for this even further when you come across mixers and start to design them by yourselves. Okay, you will find that mixers, so hypothetical stack up, right, cascade, we have succeeded the LNA with a mixer. What you'll find is that the mixer is an extremely noisy circuit. Okay, for reasons which we cannot go into now. When we come to the mixer portion, we will indeed go into it. Okay, but it's an extremely noisy circuit, which means your LNA better have enough gain to make sure that the noise figure of the mixer does not matter. Okay, fine. What does the noise of the circuit represent? So it represents the degradation in noise figure. Okay, if you take the circuit and start reducing the amplitude of the signal that you wanted to process, as you keep going down lower and lower in amplitude, at some point of time you will no longer meet the SNR requirement. Correct? So literally noise figure will limit the smallest signal that you can process using your system, using your receiver. Make sense? Okay. Now we want to calculate the smallest power that can be received. Now you are talking about a communication system. If you are talking in general about some random circuit, then you just represent it as En and In, right? Because you are going to drive it with a voltage or a current or both. Okay. Therefore you represent it as En and In. In our case, we are talking about a communication system. We are talking about signal power to noise power ratio, etc. We have to calculate the minimum detectable signal of a receiver. Okay. Okay, I'll call this minimum signal power that can be received as some P min. Okay, calculate the value of P min. Assume that the receiver has a noise figure F. Okay, so receiver noise figure is F. The gain can be G, right? I want to calculate the minimum signal power that can be received. How do I do that? The easiest way is to start from the basic definition of noise. What is the definition of noise figure? SNR in over SNR out. Correct? Okay. What is SNR in? Well, you know the signal power. What is the signal power? It's P min. What is the noise power? We calculated yesterday that it is KTB in watts. Okay, so now you are trying to calculate P min in watts. Okay, over SNR out. Make sense? Now what is the SNR out? This SNR out is literally the signal power to noise power at the end of the receiver chain. Okay. What happens if P min gets larger and larger? Not P min, P received, the power received gets larger and larger. What happens? The noise figure of the receiver will not change appreciably. Correct? KTB does not change. Right? The only thing that can change is the output SNR. The noise stays the same. The signal power will keep increasing. Therefore, the SNR at the output of the chain keeps increasing. Make sense? So, in our case, we should not just be saying SNR out. We should be calling this the SNR min. I'll call this SNR min because you are now talking about a modulated signal that you need to demodulate at the end of the chain. Every modulated signal, depending on its SNR, it will have a bit error rate. Okay. The communication signal will tell you what the allowed bit error rate is for the system. You can never have a system with 0 bit error rate, obviously. Right? Whenever you have noise, you will have a bit error rate. Okay. And it turns out that how many of you have done digital communication? None of you, right? When you study that, you will learn more about SNR. Okay. For different types of modulations, etc. For the purposes of this course, all we will say is that, do you know what a modulated signal is? How do you know? From which course do you know what a modulated signal is? ComSys. So, if you have done communication systems of some sort, you're doing it now. So, you just had enough introduction to understand what a modulated signal is. Okay. Maybe I'll quickly explain what a modulated signal is. So, normally in circuits, okay, you assume that a 2 is excited normally by a voltage or a current which is a sinusoid. Okay, but any random signal can be broken up into its Fourier components. Okay, and since you have designed your circuit to be as linear as possible, okay, the output is only going to be a linear combination of the inputs as far as the signal is concerned. Okay, which means if your signal was some random signal, you would have found out the gain for every Fourier component, okay, and found out the output. The gain does not change. The output will just be a scaled version of the input. Make sense? Okay. Now it turns out that if you were to apply instead of V cos omega t, right, I apply V of t cos omega t to my 2-port circuit. What will happen to the output? Let's say it had a gain A. The output originally would have been AV cos omega t. Now it will just be AV of t cos omega t. The circuit is linear. Right? Now imagine I applied V1 of t cos omega 1t plus V2 of t cos omega 2t. What should you ideally get as the output? okay, and so on. Okay. So now this type of signal V1 of t cos omega 1t is called an amplitude modulated signal. Okay. You can also, so you take the signal representation that we have normally studied, V cos omega t is a sinusoid. Now you get the components of this signal varying over time. And as you can see, normally you can think of the amplitude varying over time, which is what I have shown here. I could also have visualized the signal in a different way. I could I could have thought about the frequency of the signal itself varying over time. This would be FM, frequency modulated signal. I could have thought of, I think you will probably know all of this. This is called a phase modulated signal, TN. Okay. So normally the most common ways of modulating the signal are in phase, frequency and amplitude. Okay. Or a combination of them. Okay. Depending, and this is all analog modulation, what I am showing here. Now there are various types of digital modulation. Okay. So you basically think of the signal in some other vector space rather than just in time and voltage and so on. Okay. You convert that to an analog signal using the digital to analog converter. Okay. And then operate circuits with that. Send that through circuits. I think you will learn all about this in the digital communications course and beyond. Okay. Purposes, we just need to know this. Okay. What is coming in for us is a signal that has it is not just a single sinusoid. It contains a range of frequencies. Maybe if you were to look at the signal in the frequency domain, okay, maybe it has some frequency content from minus FBB to plus FBB. Okay. So this is my content of my signal. It has some bandwidth of FBB at baseband. That's all I need to know. Which means at RF, it will have FRF minus FBB to FRF plus FBB. It is not just single sinusoids. For circuit analysis, we use single sinusoids. Okay. Obviously for finding out signal to noise ratio, we are not allowed to use single sinusoids. Okay. Because the power of the sinusoid is different from the power of the actual modulated signal. Okay. Now, if you take any modulated signal, different types of modulated signals exist. If you take a particular type of modulated signal that you have decided to use for your communication, for a certain bit error rate, you can find out the minimum signal to noise ratio. Okay, which is normally specified by the standard. So now, in our equation, because I am trying to find out P min, I need to use the value of the SNR. If the SNR were not minimum at a particular value of P, that means I can actually go down lower. Right? What will happen is if I am using the power at the input of the receiver, the output SNR will keep dropping. The bit error rate will continue to increase till it hits the limit. That limit will hopefully happen at SNR min. Okay? And now this SNR min is normally in dB. Right? For a bit error rate of 1e minus 3, you may have a 10 dB SNR or 20 dB SNR, 13 dB SNR and so on. You'll have numbers like this depending on the type of modulation that you're using. Okay. So in fact P min is of course F times SNR min times KTB. So this P min in dB is called the sensitivity of the receiver. Okay, and normally it is written in this form. P min is, we already know what 10 log KT is, we figured it out, minus 174 Hertz at room temperature. The normal assumption is most of these circuits are operating at room temperature unless otherwise specified. Okay, any questions? So this is called the sensitivity of the receiver. So literally, this is the smallest signal, modulated signal that can be received by the receiver while meeting the SNR requirement. Okay, and as you can see, there are various portions, and this is in dBm. Okay. Okay, and as you can see, the various components you recognize already. Minus 174 dBm per Hertz is the path spectral density, correct? Input noise path spectral density, and then NF gives you the degradation of the. So if I were to plot it graphically, so I am interested in this frequency range. So you already have an. Okay, this is power. I think okay. So minus 174 dBm per Hertz is the input noise floor, path spectral density noise floor. Okay. If I receive it through a receiver with some noise figure F, the noise factor F, the noise figure is NF. So the effective noise floor at the output of the receiver is raised by NF, right? So if I'm receiving the signal using a receiver with noise figure NF, the effective noise floor has now increased by that NF dB, by so many dB. Above this, I need to maintain a minimum SNR to receive the signal with a certain bit error rate. So this should be the signal path spectral density if it were completely flat. But we know that signal path spectral density is never flat. Okay, so really to do, you have to integrate the noise over this bandwidth B. Okay, and then the signal power integrated over the same band. Maybe I'll show it using red. Signal power looks like this. Okay, the effective integrated value, the difference should be SNR min. Okay. If your signal path spectral density was also flat, which is very common among many newer modulation schemes, okay, you may be just able to look at the spot densities, density values, and then just make an estimate whether you're meeting SNR or not. Okay, many of the newer cellular and Wi-Fi schemes do have fairly flat path spectral densities. Okay. Any questions so far? Okay, pretty straightforward stuff, nothing really fancy. Now, I want to go the other way, right? I want to start increasing my the input power. Okay, how high can I go? Linearity limits, of course, right? So now I need to specify the linearity of my receiver. Okay, so we have looked at noise. So as usual, like I said, I'm trying to set the topic so that we leave it as soon as possible. So to design any circuit, you need to know both limits. You need to know the noise limits and the upper linearity limits. Fundamental specifications of any circuit. Okay. So if you look at linearity in RF systems, how did you actually, before we go there, how did we specify linearity in regular analog systems? Huh? Okay. So if you remember in analog, so the linearity limit that we specified was that the second term of the Taylor series should be as small as possible compared to the fundamental term. In other words, small signal approximation should be valid. That is the first one that we specified, right? Right? Imagine some of you might be audiophiles where you have used speakers, specialist speakers and so on, right? Listening to music or something else. If your volume control on that is very low, the power going out is very low, it will sound very clear. Okay? As you keep upping it, it will degrade slowly. And once you hit, so it will degrade slowly because the second order term is missing, and normally the second order term in the Taylor series rises faster than the first order term. Okay? Eventually it will degrade so much that there will be a strongly audible distortion. Okay? Eventually when you start clipping, when you start hit the limits of the swings inside your circuits, you will start clipping the signal, right? And that is the second one that you mentioned. Now, what happens when you start clipping? Even if you assume that the circuit is linear, the circuit itself is linear, right? Etc. If you start clipping in voltage and current waveforms, okay, let us say GM was linear, small signal approximation is valid, right? But you end up hitting the triode and saturation limits, which are hard limits. Okay, they are not like your second order terms of Taylor series, etc. They are hard limits. So once it starts clipping, you can see that if you put in a sinusoid, what you will get at the output is not just a sinusoid, because you now need to calculate the Fourier series components of a clipped sinusoid. Have you ever done it in any course? Signals and systems? When you studied Fourier series, didn't you? You must have had example problems like this, because this kind of clipped analysis of clipped systems are like just used all over the place. Have all? Some of you are looking at me blankly. If I gave you a sinusoid, this was the original sinusoid, but suppose I clip the top by a certain amount, and this is your new signal. Is it still a periodic signal? It is, right? So clearly the fundamental component change, but it turns out that this system has higher, not gain, voltage. This system has higher second order and third order components also. Okay. So if you start seeing systems clipping, what you will find is that you will start seeing harmonic content in the output where you did not expect it. Make sense? So you put in a sinusoid, you get more than what you bargained for, right? More than what you expected. Now, in reality, if you take an amplifier and you look at the content, the harmonic content actually starts increasing even before you hit the swing limits, even before you start clipping. Those harmonic limits, those harmonic content comes from the second order and third order, higher order terms of the Taylor series. but they are normally so small when you are applying the small signal approximation. They may even be buried under the noise floor, we don't know. Okay, but as you keep increasing it, it will slowly increase. When you start clipping, it will start increasing rapidly. So another way of describing the linearity of an analog circuit is through something called THD. Have you seen this, heard of this before? It's called total harmonic distortion. Okay, so basically what you do, you take the power in all the harmonics and compare that to the fundamental power. As you can see, this distortion as in percentage terms will keep increasing, right? So you can say at a particular input power or at a particular output power, total harmonic distortion, so much percentage. Okay, this is also a common way of doing this, and it turns out all of these are very good ways of analog circuits depending on what you are looking for. The first one, for example, is the most generic way of describing linearity, right? You want it to be linear. You are applying small. The second one tells you, I don't mind if there is a little bit of distortion as long as it doesn't clip. In other words, this is also a fairly generic definition, because what you are saying is, I want to make sure the transistor, the device does not leave saturation. So that is the way you are describing the limits. THD, on the other hand, is a very, very specific way of defining it. You are now saying whatever happens, the harmonic content in these, outside the fundamental should not be so much. For example, lot of cases, if you buy an audio amplifier, the lot of specific cases, high power cases, high amplitude cases, you will see a THD specification. Okay. Now, it turns out that all of these are not it turns out that all of these are not very useful in communication circuits for a very specific reason. If you look at my generic communication receiver that I have so far, I told you that the antenna itself is designed for 50 ohms to receive a signal in a particular band, but it turns out that the antenna is actually going to have a frequency characteristic. Okay, it will do well over my desired band. It will not do well outside my band. Okay, I take this circuit LNA. I may have an impedance matching network. I have not shown that here. I'll show it here. I may have a matching network here. This may have a strong frequency. I'll show it even stronger. It may have a strong frequency dependent function, because all the matching networks that you have seen, they are low pass, high pass, they have a certain Q, etc. Okay. What about the LNA? It turns out that majority of LNAs are also Q. What does this mean? If I actually take a receiver, okay, or in fact forget the mixer, because mixer is a more complicated block. If I just apply a single sinusoid, okay, at the input and look at the THD, it will probably look excellent if my receiver is very high Q. If I build an antenna which is extremely narrow band, if I build a matching network with a very high Q, if I build an LNA that is a strongly tuned amplifier with a very visible, what will happen is that the THD will look very good. But I know that my circuit is nonlinear. You understand? I know that my circuit is nonlinear. Okay, that will look very good. So clearly THD is not the right way of characterizing the linearity of these systems. Okay, now one of the simplest possible ways, okay, is to start. Let's go back to this. So I take a very high Q receiver and I start increasing the input amplitude. Okay, what will happen is that maybe inside the circuit the sinusoids will get clipped. Maybe the current sinusoids will, and then when they get converted to voltage, they may get filtered out and so on. Okay. So I take this here and I start clipping and then filtering it out. Okay. If you look at the power of the harmonic distortion, IQ filtering, it may look very small. Okay. But if I look at the power of the fundamental, I am clearly removing power from the fundamental of the signal, isn't it? Because I am removing during parts of the time period, I am not outputting anything related to the input signal. It's just a flat response. If I actually find out the fundamental power in this, it will not increase anymore. I may keep increasing the input amplitude. The output will keep getting clipped further and further until I will not get any amplitude at all. In fact, in the extreme, I give an extremely large signal. So the system is getting strongly clipped. What will I get at the output? So imagine now clipping with further and further, right? What will happen? It will look like a square wave, isn't it? So in the limit, it will just look like this, something that very closely approximates a square wave. Okay? If I increase the input power, that square wave amplitude will not change. Okay? So in the end, what will happen is that all of the power that you are giving in to the input sinusoid will get transferred by the circuit to higher harmonics, which then get filtered out anyways. You understand? So what will happen to the output power? It will stay the same even though I am increasing my input power. So if I were to plot the P out versus P in in dB terms, so P out would have been G times P in. Okay, G is some value that you have designed for small signals. For larger signals, of course, G just drop off to 1 slowly. If I write it in dB terms, okay, okay, so now what I am going to do, I am going to plot P out in dB versus P in dB for a circuit. Okay. So let us say I start from something very small. Okay. So it turns out that this is of course linear with a slope of 1. Right. So let me at least show a 45-degree line. Because P out in dB is simply P in dB plus G dB. So slope equals 1. Agreed? It's a straight line for small signals. Okay. What is this intercept? What is this intercept? If P in were 0, this intercept has to be the gain. Okay. The y-intercept, okay, should be the gain. As I keep increasing it, what I know is that eventually this will flatten out. Okay. And in fact, many systems, because of other nonlinearity we will encounter in a couple of classes, it may even decrease after that. Okay. We will see why in the next class or the next couple of classes. Okay. So this power is called, the output power is called the Psat or the saturated power. Okay. This is true for any generic RF system. Okay. In fact, true for any generic analog system actually. Okay. You will hit a saturation. Now in RF systems, Psat is very often defined for power amplifiers on the transmitter. Okay. Important for transmitters. Where you are trying to squeeze out as much as possible from your power amplifier. Okay. In the case of the receiver, you will never ever be able to operate at PSAT. You're already clipping so hard that you won't be able to hit any limits of, you won't be able to see, recognize the, you will, so at these points, you will need to start looking at signal to noise plus distortion ratio, or SNDR, not just SNR. Okay. Now, what is more common is to use for both PAs and LNAs. So imagine I take my original line, straight line, and extrapolate it out. This is of course fictitious, right? And I find out at what input power and output power the actual curve falls exactly 1 dB below the linear extrapolation. Okay. So I identify okay, this point where the actual power has fallen by 1 dB fictitious extrapolated curve of slope 1 is called the 1 dB compression point of the circuit. So this is called P in, the x-axis value is called the input 1 dB compression point. And this is called the output referred. So these are fairly important metrics when you design high power, high amplitude circuits. Okay. In the case of a power amplifier, P1 dB out is very important, because at the output of the power amplifier you are swinging by a certain amount. Okay, you want to deliver a certain amount of power. Everybody remembers what a power amplifier is, right? I think on the first class, I hope I drew it. Yeah, this is the power amplifier. You are trying to deliver a certain amount of power to the antenna. Okay, because you are trying to deliver very small, since there is a lot of attenuation through the air, you need to pump out a lot of power before the other person can receive with a good SNR. Okay. So normally you are interested in output P1 dB. If you are interested in receivers, you look at input P1 dB. Okay, because everything is referred back to the input, SNR, noise, linearity, etc. Okay. Okay. Now, it turns out that this is okay, but you have a problem. The problem is, if you look at the 1 dB compression point of a circuit as a metric for calculating its linearity. Okay. Now, this 1 dB compression point, as you might imagine, is literally decided by the swing limits of the circuit. This is not a small signal metric. This is a large signal metric, because you have already hit the point where output swing is changing. Now, at PSAT, the output is literally clipping. Okay, if you move back a little bit, output has not started clipping, but it started distorting, right? You don't have as before. Make sense? So, you are already at the point where the output is swinging quite a bit, very close to clipping. So, P1 dB is not good enough for us. Majority of time in the receiver, you are not going to be anywhere close to compression. Okay? Second problem. You have a second problem. If you were to take Well, let me show this. Since we drew the figure here, if you were to look at that we have we have drawn where the noise SNR, right, is shown for the minimum sensitivity. Now assume that I start increasing signal power. It looks like the SNR will keep increasing, correct? And that is in, okay, as I keep increasing power, the noise floor stays the same. That SNR out will go from SNR minimum to something larger than that. So the beta array rate will keep getting worse. But far before you hit the 1 dB compression point, PSAT, etc., it will start degrading because the the nonlinear components have started becoming larger than the noise floor of the circuit. You understand what I'm saying? So we made a small signal approximation. We have looked at that part. We have now hit the limit. We have looked at that part. But actually at some point of time, the nonlinear components will start becoming larger than the noise floor. Now the noise floor is actually very low. Okay, much lower. It is probably 40, 50 dB lower at this point compared to your signal. So you are nowhere near SNR limits. But the quality of the signal will start degrading. Okay, so in fact, if you were to draw we will draw this in more detail later. If you were to draw the SNR as a function of input power, okay, SNDR, what you will find, you will actually get two curves. You will get one curve which is the SNR itself, okay, and you will get a second curve which is SDR. The actual SNDR will do something like this. Okay, and in fact this is what we are interested in. We are interested in the SNDR in general. In fact, that is true even for analog mixed signal systems. If you characterize, let's say, an analog to digital converter, for example, you should be looking at SNDR, okay, because SNR may look like it's looking great, okay. So if you just extrapolate based on noise, it may have so many bits of resolution. All of you did analog systems, right? So you know what a data converter is, you know number of bits, etc. It may look great, the resolution looks great, but it turns out that if I operate it at higher power, the performance is degraded. I do not get as many bits of resolution as I did when I had at lower powers. Okay, so you normally look at SNDR. Okay, that is why we need a better metric, because we now, based on 1 dB compression point, we can now find out when this goes bad. We can now find out when SNDR falls below the SNR output limits. We can do that. But that is not all we are required, because we are also required to, we also want to see what happens here. Because clearly SNDR is degrading. To figure out how much is degrading, why it's degrading. I want to make sure it degrades maybe dB for dB with input signal, etc. I may want to do so many things. I may want to optimize my circuits to, reduce power consumption in that region. Okay, a real communication system you may want to, because, you need to optimize the circuit for behavior across all regions of operation. Okay, so we now need a better metric in this region. So we need to find a better way of characterizing the linearity of the circuit in that region. Whether we are far away from the noise floor, but you are far away from distortion limits, hard distortion limits also, compression limits. Okay, so in tomorrow's class, we will find out how to do that. We need something that is very sensitive. It's a very sensitive metric compared to 1 dB. Because if you look at the 1 dB compression point of many circuits which have different nonlinearity behavior, but the same swing limit at the output, they will all have the same, very similar 1 dB compression points. You understand? I take two circuits. One of them, the Taylor series term is much worse. Okay, but the output swing limit is the same. Right? The curves, SNDR curves will be very different for the two. You need a much more sensitive metric. Okay. Number two, this metric also needs to take care of the frequency dependent nature of the circuit. Right? If you define something where the term is going to go to the output and get clipped, etc., that's not going to work for us. So in tomorrow's class, we will look at what this metric is. In next week's class, we will look at what this metric is and how we are going to define. Okay. Sounds good. So see you folks next week. Tomorrow morning we do not have a class. We had 3 classes this week, right?